surface.
Oh, no one at school mine. To do the math.
Is it tethered to the surface?
Just bounced a few times. All right. Probably more people will trickle in. All right, before we start, are there any questions about things we talked about on Monday or about the homework? All right. We'll speak up if there are questions. So I'm going to continue talking about the group theory of Lorentz transformations. So this is mostly what I'll talk about today is borrowed from this book, which I think I mentioned in the syllabus. It's a book by Matthew Schwartz called just Quantum Field Theory and the Standard Model. So it's really good for certain topics. It definitely has like more advanced, more modern stuff. And it's also fairly pedagogical. So that's sort of a rare combination. So, right, let's just recall a little bit what we talked about last time, and maybe stuff that we knew anyway. But so let's just remember. So what do we mean by a group? So it's some group G. So a set. I have some set of things in it. They're called GIs, the elements of it. And in particular, they have a rule which tells me how to do Gi times G sub j. It tells me it's something. That thing doesn't have to be equal to the reverse, but there's some prescription, right? Remember the way we talked about it last time was as a table. Someone hands you a table, you have some number of elements. You just write down all possible products between the elements, and the table tells you what it is. And the idea for this thing to be a group, the main ideas are it has to have the identity, it has to have someone who does nothing in the set, and it also has to be closed so that whatever the set is, any two products will give me back someone in the set. Right? So that's the core idea of what a group is. And we had the other core thing we talked about last time was also representations, right? So we looked at that Z3 example. So it's a group that has just 3 people in it, 3 elements. But there are lots of different ways to represent it, right? The core group idea is that table, and then there's a variety of ways to represent it. Representation of a group. Some mapping of elements to linear operators. So those could be matrices, they could be functions, just something that will preserve the fact that, if I have some representation, that product of 2 representations of group elements, that should be equal to the representation of whatever the table should tell me for their product. So basically we'll preserve the group multiplication property. So right, the reason we're interested in all this is, for the case we're interested in right now, is for thinking about the Lorentz. So we haven't actually seen, I guess, yet, but the Lorentz transformations do form a group. They're a little bit bigger than rotation groups. But the thing is that we don't know how spinors transform under Lorentz transformations. We know how scalars transform. They're the ones that have sort of a trivial transformation under the Lorentz transformation. They're scalars. But in vectors, we know how they transform. That's easy too. They come with a Greek index, a mu or a nu. And so we just multiply by lambda the Lorentz transformation matrix, right? So we want to find other representations, in particular the spinor one. And also, what's our group of interest? Lorentz group, which is, may not be obvious, but anyway, there's also something called the Poincare group, which is a bigger group that includes space-time translations. But the Lorentz group for us is the group of all 3 rotations, ordinary boring rotations, plus 3 boosts. So the Lorentz group is so 3 rotations and 3 boosts. And he's the one we're going to study, for most of today. Yeah, I should say, right. 3 boosts, 3 rotations, which preserve the metric, right? In particular, I can take my metric G, usually he has some indices associated with him, but when I do a Lorentz transformation on the metric, it's not going to change any space-time invariant, right? This is the same statement as saying, that's basically what our 4-vector notation was built in with, right? 4-vector notation is super helpful for guys who carry explicit space-time indices, because if you contract things properly, then that's going to be a Lorentz invariant. Right, but we don't know how it goes for non-vector things. Right, so let's look at one particular representation that we already know about of the Lorentz group. That's called, not creatively, the 4-vector representation. So it's the way that normal space-time, I guess I'll do them downstairs. Space-time 4-vector transforms. So we know there's some matrix, and the specific form for lambda will depend on which Lorentz transformation I'm talking about. Right? So maybe I'm interested in a boost in the x direction, or a rotation in the x direction. Let's look at, let me say, for example, say you're interested in a rotation x. So the way that that's represented in 4-vector representation, so this means acting on 4 vectors. So that means this guy will be represented by a 4x4 matrix. In that case, it's 1, 1, and then cosine theta x, sine theta x, minus sine theta x, cosine theta x. Everyone else being 0. So right, I'm writing things like, this is 4x4, so we go 0, 1, 2, 3. 0, 1, 2, 3. So it's a rotation around x, which also we sometimes call 1 in our 4-vector notation. It's where we're counting 0, 1, 2, 3, right? So rotation about x is just modify things in the 2, 3 plane, right? So it makes sense. We're saying we rotate around x, so that just means x and y and z are the ones that get mixed up. But this guy has to do more than that, right? He's not just rotations, he's also boosts. If we had a boost in the x direction, the way that's represented is, and we did talk about this, I know. Actually, yeah, maybe we didn't talk about it in Shanker. I mean, we must have not. We're doing all non-relativistic stuff. But maybe you know the story, right, that you can think of space-time, you can think of a Lorentz boost as something like a rotation, but it's a rotation that mixes up space and time, right? And also, instead of being cosines and sines, it's a hyperbolic cosine and sine that enter. And they come without anyone having a minus sign. sense it's easier to remember. And 1, 1, and everyone else 0. Where this thing, for example, this cosh beta x, this is gamma, the same gamma that you know in the 1 over 1 there. Square root of v squared over c squared. This is sometimes called the rapidity. Anyway, it's like an angle in space-time. Right, so this is just, remember the way to think about it, right? Rotation, obviously, is just someone now is telling you how your original coordinates rotate into each other, how some part of your y and z get rotated into a new y and z. And a boost is a similar thing, but now its time is playing one of, plays an important role. You're rotating part of your space into time and part of your time into space. But, right, let's not forget, right, what we're after, right, is something beyond representations, right? This is just a helpful way for us to think about it. And there's a standard path for figuring out the core group structure, which is look at an infinitesimal transformation. We had that same strategy too in the Shankar book. We were looking at just how do we develop spatial translations and time translations and stuff there. Because once you understand the infinitesimal case, then you can build up any arbitrary finite transformation. Alright, so we want some rep independent info about the Lorentz group. So let's consider infinitesimal transformations. And School of Minds is there now, I think. Let's look at infinitesimal Lorentz transformations. So what we'll actually do, so right, remember this is, like I've been saying, this is something where I'm thinking of a particular representation. I'm thinking of how does the Lorentz transformation manifest itself on 4 vectors? Well, we look at 4x4 matrices. But what will happen is when we look at infinitesimal transformations, we'll be able to extract some information from this representation-dependent thing, but that information will ultimately be representation independent, which is funny. So it'll allow us to write down the core commutation relations for the Lorentz group, which are true for anyone's representation. Because remember, the idea is that the group is the multiplication table, or the information in the commutator. So we should be able to get everything once we have those commutators. We'll know everything about the group. Right? So we're going to consider infinitesimal transformations to extract the group information away from the representation. So the way to do this, with this representation is easy. So I only wrote down 2. Remember, there are 6 things we can do in the Lorentz transformation. 3 different rotations, 3 different boosts. I just wrote down 2 of those 6. But if I do an expansion where these angles are small, it's not hard to do 1 by 1, right? I just do a power series. So I do 1 minus theta squared over 2, theta minus theta cubed over 3, etc. Right? I'll just keep the lowest order thing to see what happens. So when you do that, I'm not going to do it all. I'll just write down the answer. So the time component, right? Time won't care about any of your rotations, none of the thetas, but it will care only about boosts. And in particular, is only going to care about the one involved in the boost, right? It's easy. In the boost case, it's in the x direction. you care about that boost in that direction, whereas rotation is a little different because we're talking about rotation about the x-axis. So it'll involve the other coordinates. So if I look at how the ith spatial coordinate changes under a Lorentz transformation, there's some part coming from a boost also, but I also have the rotation part to care about. So the reason too for invoking that guy, Mr. Epsilon ijk, is just as you have to, because of the way we're defining rotations, right? So remember, he's totally anti-symmetric, so he's only going to be non-zero for 1, 2, 3, and permutations of that. So if I'm interested in x, he's saying you have to have j and k be not equal to x, right? Which is exactly the property that that boost has. So this is general, and that summarizes all Lorentz transformations, right? All infinitesimal Lorentz transformations, whether they're from boosts or from rotations. So we could even write this out slightly more explicitly, maybe too explicitly. Or we can write a 4-vector notation. I'll pull out an I. Sum on 1 to 3, theta I. So now what we're going to do, this is the general strategy, which I'll talk about. The general strategy is whoever is in front of your small parameter, that is basically the thing that we're going to call the generator of the group. It's the non-trivial part that comes from this infinitesimal transformation. Sorry, let me not say that's me new. Doesn't matter. The J's we already sort of talked about. They're the generators of ordinary rotations. But now we also have who's the guy who's coming, in front of boost, the infinitesimal boost. We call him also not very creatively k, just because k comes after j, I guess. But we can summarize this in this basis, in this representation. We can summarize explicitly the 6 generators. I'm only going to write them down once because it's too much writing, but I want to write it down in case you want to check things. And I'm apologizing ahead of time for writing it down. So 1 minus 1 is 0. 2 is I. Yeah, this one actually I do have to write down all the zeros. 0 minus 1. And J3. So by the way, before I write down anything further, remember how you get these, right? I'm just going to write them down and not do them all, show you how you get all of them. But for J1, right, this is the rotation about the x-axis, because we're calling x the first component, right? So you can get it exactly from this, right? So the cosine part, lowest order is just a 1. And that's the do-nothing part of the matrix, right? That's part of the identity. So we're not interested in that. Identity is the identity. So the only part that matters is the sign part. That's the interesting thing from rotation. And the lowest order is just equal to theta, right? So, and in particular, those final 2 things should be different by a sign, and that's exactly what they are. The I is some convention, but in other words, right, from just staring at this ordinary transformation that we know from forever ago, we can extract out what a representation is for the generator of rotations around the x-axis. So this is the smallest thing, that will represent a transformation about x. So we can do the same thing for the other rotations, J, 1, 2, 3, and also for boosts. The only reason I want to, there are a couple of reasons. I want to give you at least a path to calculate everything explicitly if you want. But thankfully, we're not going to need to know them most of the time. Some explicit form for them. And let me quickly write down K1, 2, 3. You can also get K1 from the explicit matrix I just wrote. But most of the time, they got a bunch of zeros. I hope all of the time. Because there's only two axes they ever care about. And K3. I'm also writing them because Mr. Peskin doesn't give them to you. And I think it's helpful if you want to show what we're about to write explicitly. So, right, in other words, these have all the core information of the Lorentz group. It's a bit cumbersome, for sure, right? It took a while just to write it down. But from these you can construct, for example, any particular any finite Lorentz transformation. We're using the same rule we use also in non-relativistic quantum mechanics, that you exponentiate the generators to the power of that angle also. Now these don't have to be infinitesimal ones. So you could show this, right, from looking at this, these small infinitesimal things, and you can make this formal by saying I'm going to apply it n times and take the limit of n going to infinity, and the way you get the exponential out is that 1 plus something n to the to the n times is like the compound interest formula or whatever. So you get an exponential.
Are there supposed to be i's in both there and on the?
Oh yeah. Sorry, here.
Yeah.
In the case, yes. So we did need it too because in, for example, here, right, there aren't actually i's appearing, so we need to have them both places to.
Oh.
Yeah, it's a funny convention, but it'll make more sense in a minute. Well, maybe it will. So we're right. Let me also say this is a general sort of thing that also, and also part of the reason for talking explicitly about Lorentz transformation, group properties, and all this is that all of this formalism is general and very helpful for understanding the forces in the standard model. Because they're also based on these types of groups. So it's a totally general way to write a finite dimensional representation, group elements. So you can rewrite your group elements as an exponential e to the I some numbers times some operators or some group generators. So these guys are the group elements. And these things are the generators. These are just coefficients, basically telling you how much are you transforming by, the equivalent of the angle in a general case. So sometimes to people, we're not going to make a big deal about the distinction between Lie groups and Lie algebras, but technically these generators live in a Lie algebra because you can add them as well as multiply them, whereas the group elements are really just defined by the multiplication table. We don't know how to add them in a sense. But we'll never need to worry about the difference really. Right, so I also said something maybe you've heard of, which is a Lie group. So these are certain types of groups. There's also a person I don't know anything about, Lie. But this is a particular type of group one that has an infinite number of elements in the group, but a finite number of generators. So, and they're very important for the standard model. So, infinite number of elements, a finite number of generators. And very important for the standard model, not just for studying Lorentz transformation. So there are, and we'll talk about names of groups and things a little bit at least. But quantum electrodynamics, which we'll start studying pretty soon, is connected with a particular elite group called U1. So this is also just a group of transformations that lie on the unit circle. But ultimately, studying that particular elite group really lets you understand a huge amount about QED and the symmetry structure of it. The weak force is connected with SU2. This is the group of Pauli matrices, which has a very funny connection with the Lorentz group, which we'll see in just a minute. And also the strong force is SU3, and the Lorentz group sometimes is written as being the kind of group, right? Because we're almost talking about rotations in a four-dimensional space, in space-time, but it's not quite rotations, right? Boosts are kind of weird. For one thing, they're not cyclic, like rotations are, right? Cyclic, if I do, rotations, if I do more than 2 pi, I get back to the same spot, but boosts aren't like that, right? Boosts are kind of weird. So the way people write that, instead of calling it SO4, which we would be if everything was Euclidean, and time wasn't special, we instead call it SO3, 1. Just to denote that it's the rotational part is normal, Euclidean, boring, but then there's one coordinate that's kind of weird. That's the way that we represent it. Okay, but instead, now going back to these generators we wrote down, instead of carrying those around all the time, we can instead summarize all the properties of the group. Remember, they're supposed to be inside those guys, right? We started out with a particular representation. Now we have this, their infinitesimal amount of boost in the third direction, for example. We can summarize all of that information without having to write out 6 4x4 matrices every time with just commutators. So the reason I wrote them down is that you can check the commutators I'm going to write down are correct. Right? I'm giving you at least the path for how you would do this. I'm not going to actually do it because it would take too long. But it's also a general thing that for the algebras, they're determined by their commutator. Really. And once you know that, you sort of know everything. That's the core information. And for the Lorentz group, I'll write it down. So if I have a commutator between 2 j's, we know actually the answer, right? We talked about this last time. We talked about it even in Shankar. Just, it's going to give you the third rotation with the epsilon ijk. So you definitely can check that if you want, right? You could do j1 times j2 from that explicit representation we just wrote, and then minus the reverse, and you should get back only the third component with the I. But this is what makes it a group, right? Is that what happens if I do commutator the generator of rotations with the generator of boosts? The funny thing is that gives me a boost. First of all, it's not something else, right? It would be bad if it gave us something that was neither J or K, then it wouldn't be a group. And the final important one, I guess I'm almost ready to see if I'll stuff it in the bottom. If I have 2 boosts, this is what makes boosts funny. compared to rotations. Commutator between two boosts is a rotation. So they're really mixed up. We get a J out of that commutator. And yeah, the minus. Everyone has an epsilon ijk. So is it clear at least how you would check that from those matrices, right? It's a lot of work to check it. But that's why we're going to use that notation instead. Right, and also, the other nice thing about writing it like this is it also shows you, obviously, that rotations are a subgroup. Boosts are not a subgroup. Right, boosts automatically, I just want to think of, if I wanted boost to be a subgroup, I just compute their commutator, but then I get someone who's not a boost, right? The rotations are very special compared to boosts. Boosts are sort of the guys that break everything, make it a little more complicated. So there are other representations. I'll just talk about them very briefly because sometimes they come up, but we're not going to follow it right now. Right. So, right. Now, let me just emphasize, right. This really, we can call this, these are the generators of this SO3 of Lorentz. So that's the core information about the Lorentz group, right? With that, you could do everything. Yeah. So another representation that sometimes is useful is more of an aside, because we'll come back to this later. So it's a two-index tensor representation. So I can write all the generators in one big matrix, which we call just V, and you just combine all the boosts and all the rotational generators all in one big matrix. Minus J3 minus J2, J3. This one actually is related to something we wrote last time, and it makes it more clear how this is connected with ordinary angular momentum generators, or rotational generators. Right, note, by the way, each element here, remember this guy, right? We had a representation for him before. He was a 4x4 matrix. So this is a really, really big matrix, right? It's a 4x4 matrix where each element is a 4x4 matrix. But note that each element is a 4x4 matrix, so it's 16-dimensional. So right, if I was interested in the 2-3 element of this matrix, that's J1, because remember I go 0, 1, 2, right, 0, 1, 2, 3. So the 2-3 element would be this J1. And then, right, then Lorentz transformations can be written as this V representation as exponential e to the I, right, sigma mu. So these are the generalized angle. That's an even more compact way, sort of, to write down all Lorentz transformations in this big matrix. So then if I wanted to, I could work just with the commutator of that object, which is even weirder in a way. So yeah, let me not actually write down the commutator because we won't need it. this is very much connected with representation we knew before. So it's really it's connected with the infinite dimensional representation that acts on functions. So we kind of guessed that from before, remember. I'll write it down. This is the generalization of three angular momentum. So remember, angular momentum classically is x cross p, right? So if we take x cross p, just in, say, non-relativistic quantum mechanics and make x and p operators, you convert, for example, in position representation, right? You convert p into some derivative, and last time we were arguing, maybe that's a way to guess at what the generators are for the Lorentz transformation when you're acting on functions. So this is really connected with the same tensor representation, which we will come back to, but there's a more important point to stress right now, which has to do with these generators. So actually, let me leave them here. Are there any questions about all this stuff? There's a lot of formalism, but things all of a sudden become easier because of a sort of crazy fact, which is that these generators, so this is basically the Lorentz group connection to SU2. So it turns out that the reason that all these are epsilon ijk is sort of a clue. One of the other places we've seen commutators come with epsilon ijk's is the Pauli matrices. And it turns out we can really just rewrite all of our generators for SO3, 1 for the Lorentz group. We're going to rewrite them as Ji plus minus 1/2 Ji plus minus I Ki. So we're just going to take a different linear combination of these 6 things. So right now we can forget about those matrices we wrote before that were big and cumbersome. If we want it, all we have to remember is that, these commutators. So we can check with this change of notation, if we now start working with these guys, the plus and minus j's, which are some linear combination of the originals, commutators are even better than before. They are the I consider commutator. Well, let me actually write it better, make it more clear. If I consider the commutator between 2 pluses, for example, they just give me back K plus. And the same is true for J minus. And the best possible thing happens if we consider plus and minus, so that it's 0. So it's a very weird fact. It's saying, look, if you choose this way of writing your generators, the Lorentz group, which seems kind of weird, involves boosts and they're connected in some weird way with rotations. If you just rewrite your generators, it's just SC2 twice. It's just the same thing that Pauli matrices satisfy. So people will write that this is equivalent to 2 SC2s plus And actually, we know a lot about SU2 from studying angular momentum and Jankar, and also from studying ordinary rotations. SU2 is actually also the same group as SO3, just ordinary 3 rotations. Right, that's what also another way of writing what this is, right? These are just our ordinary, same commutation relations we have for, X, Y, Z rotations. Exactly the same commutator. So this gives us sort of a lot of power actually. It lets us write down representations of the Lorentz group based on the information that we already know about for SU2. All right, any questions?
It's the plus symbol, but again, it's just and.
Direct sum. So we'll see what it means actually. In terms, it basically means treat them separately. Yeah. But it's equivalent to basically 2 copies of SU2 that don't talk.
Because that bottom commutator is
Yeah,
0.
exactly. Yeah. So boosts. That's not obvious looking at the previous set of commutation relations. Because boosts were all messed up. They were mixing in with rotations. Right. But now we can. Right. We could use all our info about SU2 to produce Lorentz representations. So one of the things that we know is that for SU2, so if you started out, remember in Jankar, if you had angular momentum J, you're going to have a degeneracy of 2J plus 1 elements. So remember this thing for the magnetic quantum number in non-relativistic quantum mechanics could go from J to total angular momentum down to minus J, because 0 in integer units, so since 0 is there, it's 2J plus 1. Actually, even more important thing is that each representation is controlled by a half integer. We'll write it as little j, just like we did in non-relativistic quantum mechanics. And this would have 2j plus 1 elements. So now what we're going to do is label all possible representations by what's your quantum number associated with the first SU2 and your quantum number associated with the second SU2. So we can label it by just these 2 numbers, basically. Right. Let me just write it. So, we won't actually need all of this full power. We'll probably come back to it when we talk about spin 1 fields. But now, any representation of SO3 comma 1 could be labeled as just A comma B, where this is your we have called this SU2 A and SU2B. So we're just saying what's the J associated with one of the SU2s. We're just going to order them arbitrarily. And what's your total angular momentum associated with the other one? So what we care about for spinners are each of these being, either one of these being 1/2. But we'll see that there's sort of two options, not obvious. If we care about spin 1/2 fields, it's not clear which one we want. Do we want A to be 1/2 or B? You might already know the physical importance of it, but it's saying that what we're connect this to eventually is that fermions can come in two varieties. It could be left-handed or right-handed. And certain mass terms will mix them. So we're going to focus on spin 1/2 representation. But you can build up any arbitrary ones using this same method, just by connecting it with SU2. I think we're interested in J equals 1/2, right? We're going to have two options. It could be 1/2 comma 0 or 0 comma 1/2. So let's see what this really means. What do we mean by that? Some of these things sound abstract when you're first writing them down, and then make more sense as we look at something more explicit. Right. So also, right, if we're interested in J equals 1/2, so we're going to be interested in finding some 2x2 matrices, right? So the dimensionality will be acting on something that has two components, 2 degrees of freedom, which sounds good. Like we know about from non-relativistic quantum mechanics, a spinner is a 2-component thing. So we want 2x2 matrices. We need 2x2 matrices, and if ones that satisfy the same commutation relations. But we already know 2x2 matrices that do that, which are the Pauli matrices. So these are Pauli. We need them to be divided by 2 just to have the right normalization in the, because we define our commutation relations to be, give me back a generator with no extra factors of 1/2 or anything. So we're now going to start working with generators that are the Pauli matrices divided by 2, then we get that this thing which is called the structure constant for this group is just the epsilon ijk, the Levy Civita, I don't know how to pronounce that totally anti-symmetric 3-index guy. So what this really means, these two representations that are 1/2 comma 0 or 0 comma 1/2, what they mean, let me take the first one. That representation means that J minus is represented. Remember, it has to be something 2x2. So it means that our J minuses, these are 1/2 of the total of SO3 comma 1. They're represented by just the Pauli matrices. And the other half is represented by even more trivial representation, which is 0. They don't care at all about those generators. And the opposite's true for the 0 comma 1/2 forever. Now, J minus is 0, and J plus is Pauli matrices divided by 2. Right. We can also, use the fact that J is equal to, go back to our original definition of what are these things, right? There's some combination of the real rotation and boost operators. So I can get back the real boost operator by just doing the sum of J plus and minus, and the boost K is I times the difference between J minus and J plus. So I could get two, let me separate the two representations. This is the same thing too, as saying for the 1/2 0 that J is equal to 1/2 sigma, so is K with an I. So that's ultimately, we want to work with, I guess, slightly more physical generators, ones that we know how to relate to real rotations and boosts. That's what we would use. And in this other representation, it's almost the same, but with a minus sign. The rotation generators are the same. It's like always, boosts that make everything weird. Okay, it's kind of funny, right? We got a little more than we bargained for, right? Because we thought this also will help. You know, we thought we were just going to figure out how do we deal with spin 1/2 fields, and now we have these two representations of how a spinner can transform under Lorentz transformations. So how do we choose? This ultimately, right, should get us thinking that, remember when we had this quick way of driving the Dirac equation last time? It was sort of miraculous and didn't explain anything. One weird thing was that you need 4x4 matrices and you need them to act on a 4-component object. So this gives us a clue, which we'll see shortly, how we get a 4-component object out of spinners, is that we have these two equally good representations. So we're just going to stack them on top of each other. Stack two component things on top of each other. We'll have one 4-component spinner. Yeah, so these guys are the ones called right-handed sometimes. These are called left. So we can finally go back, right? We could put in, remember our rule is for figuring out how something is transformed. We do take the generators, take e to the I of the generators, basically, right? So we have two separate rules, two separate transformation properties. For spinners. So if he's say a right-handed spinner, it's going to go e to the 1/2 I sigma j theta j plus beta j sigma j times our original field. Right, so this is just using that same thing from before, right? We just do how much am I changing it by? That's controlled by things like theta or beta. And now the generators, in both cases, are controlled by Pauli matrices. Just have to worry about, is it with a plus sign or a minus sign? Oh, maybe I mixed up the. Yeah, I think I mixed up the name. So this would be the other one. Okay. So left-handed and right-handed would be the same if it wasn't for boosts. So we'll see also why they have these names, how that's related to the physical meaning of a boost. I mean, yeah. Okay, the whole reason too, for our immediate purposes at least, besides it being relevant for any other groups we'll encounter in particle physics, like SU3 or for the strong force or SU2 for the weak force, It also is immediately helpful for us because we saw, just looking at the Dirac equation, that thing that we got in this funny method has to be Lorentz invariant. But it's Lorentz invariant in a really weird way because you're contracting a matrix on a 4-vector of derivatives. We know how 4-vector of derivatives transforms into the Lorentz transformation, but how do I really contract it with a matrix in a right way that makes everything, when it acts on a spinner, it makes everything Lorentz invariant, right? The spinner has to have weird transformation properties, which we finally saw. We know now how it transforms under a Lorentz transformation. It's a very non-trivial way of transforming. So this information also helps us build up Lorentz invariant Lagrangians, right? Our Lagrangians gotta be, this is ultimately leading to the a better way of deriving the Dirac equation, which is just trying to guess at it basically from the properties of Lorentz invariance. So let's look at Lorentz invariant Lagrangians, and we'll see what properties we need. So first of all, right, especially in the way we're thinking about this right now, is that we have these two equally good spin 1/2 representations. We don't know which one is right, or if they're both equally right. We don't really know that yet. So let's imagine, right, what would be great is if we could just throw one away, because I don't like having twice as many things to worry about, right? Maybe we could start, like we have sort of for scalars, maybe one can write down just a 2-degree of freedom Lagrangian spinners. That's Lorentz invariant. So let's try to guess what, generically you have things like a mass term and a kinetic term. And let's try to make him, at first, just a function of right-handed fields. You can choose left or right, it doesn't matter. Let's just choose one. So, first of all, how do we guess even the form of the Lagrangian? Maybe you want to take sort of some ideas from our studying scalar fields and guess that he has to be quadratic in the field, right? So also thinking about it in terms of Feynman diagram language, remember, when we had something that had 3 powers or 4 powers, those are describing interactions, right? 3 powers of the field looks like a cubic vertex, a vertex with 3 lines, and 4 powers of the field looks like a vertex with 4 lines, and so on. But a mass is just telling me how to propagate from one point to another, right? So I can think of that as a vertex with 2 lines, which is a line. But a vertex with 2 lines then should have 2 powers, right? So anyway, it should be something quadratic. So our first guess is that for the mass, let's focus on that term first, that it should be something, and also I want to make it involve only the right-handed field, right, to start out with. Let's see if that's possible, and maybe also, because I think these guys are going to be complex, maybe I want to have this look like some sort of normal sort of invariant that I encounter. I'd have to take a Hermitian conjugate, something like that. So it turns out we could figure this out from looking at the Dirac equation with the mass dimension. Remember our way of computing dimensions for things. We want the Lagrangian to have mass dimension 4, because the action has mass dimension the action is dimensionless. It has units of h bar, which is 1 for us. And, right, remember action is like a 4 derivative of Lagrangian. So I know this is unitless, this has units of 1 over mass to the 4th, so Lagrangian has mass to the 4th. So So it turns out, you can figure out from the Dirac equation, this has mass dimensions 3/2, meaning that this term has dimensions 3, so that thing is a mass. So let's call it that. They'll even get a subscript. Well, no, for now, let me just call it that. Really does have the right units of mass. Okay, but now with this arbitrary transformation, we can check, is this Lorentz invariant? Right? At least now we know how to do it explicitly. Before we didn't know, we just knew some funny combination of the Dirac equation was Lorentz invariant. So let's check if this L mass term is Lorentz invariant under an infinitesimal transformation. Makes it easier. So exponential is 1 minus the stuff in the exponent. We don't care about the 1. So if we throw out the 1, we look at just the deviation, say, right? If I just focus on the part that's different from this transformation for something infinitesimal, the small new part of the right-handed field is just, I did. Sorry. Changing that back. So the right-handed field is I theta j, sigma j, and just times the original field we have back. You can also check, because what we'll need to check the invariance of this, we also need to know how much the dagger of the field changes by. So it's 1/2 of a minus I theta j, and sigma r dagger. So this is enough information to see already. It's not going to work. It's not going to be invariant because, let's look at, say, for example, how much does this bilinear, this combination of fields, how much does that change under a Lorentz transformation?
AR times DR.
Well, so
product rule.
yeah, let me think about there being sort of 2 terms. So let me think of, variation of the, variation of the conjugate field times the non-varied field, and then plus conjugate field times the variation. Right, so there's sort of 2 terms to worry about. So anyway, now I'll get about my general transformation. We're just looking at infinitesimal ones. So from this claim, we can see right away, this thing is not Lorentz invariant. So that variation you can sort of see from staring at this. When you add them together, right, the parts having to do with angles are going to cancel, but the part having to do with boosts won't. So the boosts always is the problem. They're always screwing everything up. If it wasn't for boosts, this thing would be invariant. That's a powerful physical statement, actually, that we'll come back to. But this is, if you just do that addition there, which I'll not write out, it's really straightforward. You can sort of tell, I think, from just looking at it. This is what you get that's left over. That's definitely not equal to 0. So unfortunately, and you can check also actually for the, kinetic terms are actually fine, but mass terms do screw things up. So Turns out actually there are two choices for the mass term. Right now we're only going to talk about one because it's the one that's most relevant for the fermions of the standard model. But the mass term can, right, also Lorentz invariant is something called the Dirac mass. We first just get this combination for masses. So remember we started out with the idea, I want to forget about the left-handed one. I don't like worrying about two spinners. If I could only afford to deal with one, that'd be better. So I write down a mass term only involving the right-handed one, and that turns out not to be Lorentz invariant. There is a way to write down the Lorentz invariant mass term actually only with right-handed fields, which is called a Majorana term. We're going to postpone talking about that though, because Dirac masses are more relevant for all the fermions in the standard model. Maybe neutrinos are Majorana. But for the electron, for sure, the quarks, they have mass terms like this. So let's check. So I really should also write the other Hermitian conjugate. Sorry, left. So let's check that that thing actually is okay. So if we were to look at each term by itself is Lorentz invariant. You only need the other one around just because otherwise the whole thing wouldn't be real. The sum. So just write down what the terms are. We have 1/2 minus I theta I minus beta sigma I and plus, oh sorry, I think I left out, oh yeah, of course it has to be. Sorry, right? Side left dagger, 1/2 I theta I plus beta sigma I sigma right. Right, which does just right away explicitly cancel out. So this term does indeed seem to be Lorentz invariant, this mass term. So okay, step one, we at least know one Lorentz invariant mass to write down. You could check that the other term is also Lorentz invariant. They're separately Lorentz invariant. And the last important thing about this, the minimal ingredients for some equation of fermions, right, would be a kinetic term and a mass term. I mean, really minimal would be just kinetic, so maybe we should have started with kinetic, but so I claim if I take the I as conventional, if I take this combination of ingredients, this is Lorentz invariant. Lorentz invariant kinetic term, or this sigma mu, the new thing, it's just taking the Pauli matrices and making them their own 4-vector, where the zeroth component does nothing. So if we want to, right, remember our rules for these indices, right? What this means is that the thing without the derivative, the rest of the vector, which I'll call v u subscript, sigma mu. psi fields. So this must transform as a 4 vector. For this thing to be Lorentz invariant, right? This thing doesn't transform, right, in any obvious way. There's just some Pauli matrices, which are always the same for whoever's Lorentz transformation in any frame. But this right combination of spinor degrees of freedom, I claim that that thing must transform as a 4 vector. And if it does, then this whole thing is Lorentz invariant, right? Does that make sense?
Not quite.
So just by our notation, basically, right? So this, I mean, we've always had, you know, I write down anything like this. If they're true 4 vectors, it's manifestly Lorentz invariant, right?
Yeah.
So that's the same statement. That's what I'm saying. So, you know, I'm grouping these guys together willy-nilly at first, right? It looks like out of nowhere. But that's the non-trivial claim, right? So if this thing is Lorentz invariant, if that's so, it must be that this has the right transformation properties as a 4 vector. Does that make sense?
Yeah.
So let's, so for that claim to be true, we need to check that d mu has, transformed as a 4 vector. So actually, I should have highlighted before. So V0, the zeroth component of this, we secretly checked already, right? Sigma of 0 is 1. So this is that mass term that we looked at before, right? So we actually know how that thing varies. We don't need to redo that. I'll write it down. Again, we saw that the way that this varies in our Lorentz transformation is proportional to something having to do with boost. And we also want to check the spatial components of this 4 vector. So, right, from before, we saw psi r dagger psi r, the variation of the thing relevant for V naught. That was just equal to a boost beta sub I, psi r right, with a sigma matrix. In that case, right, that was coming from, because those were generators. And non-trivial part, which I'll just write down the answer for because we're running out of time. I want to look at also the variation of the spatial part. So once the dust settles, this is equal to beta psi dagger psi minus theta j epsilon I j k psi r dagger sigma psi r. And again, the way you get this is just doing the same things we've been doing, right? We just look at this product, we know how each of these things transforms under a Lorentz transformation, so you just have these two terms, you sum up, and the way you get out epsilon I j k from doing this is just from the fact that the commutator for sigma matrices will appear. That's how you generate that epsilon I j k. But anyway, it's not, may not look like it, but this has the right properties of how a 4 vector transforms. Yeah, so let's say, it's easiest to just write this down. Remember how a 4 vector is supposed to transform. actually earlier in the class for how 4 vector transforms. The zeroth component will only get a little bit from a boost, and we'll get in particular stuff having to do with the spatial direction, right? That's the statement that boosts will rotate sort of space into time, and time into space. But rotations also rotate space into space. Of course, so they appear too. So you can check by eye, with everything that's on the board, how the zeroth component transforms. Now it comes up with a little bit of the spatial part, right? Times beta. And the zeroth component, sorry, the spatial component, the 3 component part, gets mixed up with both the original zeros and the spatial components. So this thing definitely works just like a 4 vector. Which means we can write down a Lagrangian, which is a funny, cumbersome looking thing, but it's actually exactly the same thing as the Dirac Lagrangian and the Dirac equation. Because we can always get the equation from the equation of motion from the Euler-Lagrange equations from the Lagrangian, right? Side right dagger, side left, plus side left dagger, side right. So we checked this for the right-handed combination, but there's you can also do it for the left-handed. Find out the kinetic terms advantage. So since we're running out of time, we'll stop there, but we'll start going back to doing field theory, because now we're just writing down the Lagrangian, but now with this deeper knowledge of Lorentz transformations and representations of them. But next we could, well, first I also want to show that this is really the same thing as this encodes all the information of the Dirac equation, and then we'll quantize it. But notice if not for the mass terms, right-handed and left-handed fields, they just propagate separately. It's really this mass term that lets them mix up. So if we could set that term to 0, life would be much easier. Massless fermions. Would really produce it as a left-handed state, it would always stay left-handed. Yeah, and maybe we will talk a little bit too about, I think Peskin does, talk about the other type of mass term you can write down that lets you connect left-handed to left-handed states so that you don't have this, or right-handed to right-handed, so you don't have the mixing that the Dirac mass term has. But this is the kind of term that appears for the electron, for all the standard model particles, except for maybe neutrinos. We don't know the right mass term to write down for neutrinos. All right. Any questions about this stuff? So we'll start going back to doing real, or not real, but quantum field theory. More group theory stuff. Very soon. We'll look at propagators for fermions and all of that. Yeah. All right. Have a good weekend. Let me know if there are any questions on the homework.
What's that?
I was lazy. I didn't cook yesterday, so no leftovers.
I promised Danny I would not eat pizza today. Go home. Good luck. And that's pretty easy class,
Yeah, so let's pick it up.